Okay, good morning, everybody. Welcome in this new recording on determining latitude. In the previous recording, I explained to you how you can calculate your latitude at culmination. Now, today, we'll talk about determining latitude with the X-Meridian method, as you can see here. And the second method will be determining latitude by Polaris. Now, when is the X-Meridian method being used? Well, at certain moments, it will be possible that you cannot see the sun at the moment of culmination due to bad weather. Maybe the sun would be covered by clouds or something else, and so you cannot observe the sun at the actual moment of meridian passage, but you can observe the sun just before or after meridian passage. And the method to be used then is called the X-Meridian method, because the sun is not exactly in your local meridian. It is a little bit before or after the local meridian, so your local hour angle will not be 0. It will be very small. The polar angle will be very small. And so, because you're not exactly 100% in your local meridian, you will need to apply corrections. So you can use this shortened method for determining latitude, but you will have to apply corrections to the altitude that you are observing of the sun. Voilà. And this is demonstrated here on this drawing. You see that when the sun is in your local meridian, the sun will be in this meridian, but it can be very well possible that there are clouds or whatever and that the sun is not visible, so you will have to observe the sun just before or just after, when it's on the other side, after meridian passage. And you will see that the altitude that you get from the sun, that you will need to apply corrections, because it will not be 100% exactly the same altitude as the altitude of the sun at the actual moment of meridian passage. And that's what this method is all about. So voila, as I told you, sometimes it's impossible to observe the sun at the exact moment of meridian passage due to weather conditions, because the sun at its peak height means the moment of meridian passage. We all know that at the moment of meridian passage, we are at true noon. And at true noon, the sun is at its maximum altitude, and that our local hour angle is 0 degrees. That we talked about last time. So it may be possible that the sun gets covered by clouds at its peak height. So we end up with a site that is near the transit, but not exactly at the transit. Voilà. Fortunately, we have a method for this. So the near transit of the sun, or the observation of the sun near the transit, it doesn't necessarily mean a miss on the determination of your latitude, because a correction method has been developed for this, which we call the X-Meridian method. Because we know the paths of our celestial body, they are well predicted, and when we have our accurate time and our dead reckoning position, we can determine what the height would have been, the height of the celestial body would have been, if we had really actually seen it crossing our local meridian at the real actual moment of meridian passage. Okay, so we can, using our time of observation and our dead reckoning position, and knowing that we know the paths of the celestial body, they are predicted. Where are they predicted? In our nautical almanac. And so, knowing all this, what can we do? We can determine the altitude of the celestial body that it would have had when the body would have been really crossing our local meridian, and would really have been at the moment of meridian passage. So, and when we want to determine our latitude with this method, we are using the X-Meridian method. X means because it's not really on your local meridian. Voilà. So if the body is observed when it is near the meridian, then we know that our local hour angle, our LHA, will be small, because it's actually near the transit, and we know at the moment of transit that the LHA is 0 degrees, and that our polar angle subsequently is also 0 degrees. Voilà. And so the latitude in which the position line intersects our dead reckoning latitude, well, that can be calculated. The latitude that we obtain with this method will be our apparent latitude. Okay, it will not be our true latitude, because we are starting from a dead reckoning position our longitude, which is not our actual true longitude, but it is our dead reckoning longitude. So it's important to know that the latitude that we calculate with this method, it's not really the true latitude of the ship, but we will see that the ship will be on a position line which is perpendicular, which would be nearly east or west. Voilà. So a position line which is nearly east or west is, voilà, when we have a position line that goes from the east to the west, we have actually almost a parallel of latitude. We don't really have 100% a parallel of latitude, so the latitude that we determine with this method will not be really our latitude, but it will be, voilà, we will have to draw a true bearing, which will be either almost north or almost south, because we are near meridian passage, and then the position line that we draw perpendicular to that bearing, that will be our line of position. And so we will be somewhere along this line of position. The only thing that we need to determine now is where we can draw this line of position. Where should we draw it? Should we draw it here or should we draw it there? Well, I can already tell you now that we will have to draw it based on our dead reckoning longitude. So we have a dead reckoning longitude somewhere, voila. And then with this method, we determine our apparent latitude. I will make a new drawing, but it'll get clearer later on. So we start from our dead reckoning longitude, excuse me. This is our dead reckoning longitude. With this method, what will we determine? We will determine our calculated latitude, or apparent latitude. Voilà. And so there we find the point where this latitude intersects with our longitude. And so starting from that point, what will we have to do? We will have to draw our bearing, which will be nearly north or south, depending on where we are, depending on our latitude and the declination of the sun. And so perpendicular to that line, to that true bearing, we will draw our line of position. And so the ship, that is what explained here, the ship will be somewhere along this line of position. Okay, we will not be on this line. This is our calculated latitude, but this calculated latitude will tell us where to draw the line of position. Voilà. And so our ship will be somewhere along the line of position. The ship will be on the position line, which would be nearly, this is this one here, it is nearly east or west. It's not exactly east or west because our sun is not really at the moment of culmination. If the sun would have been at the true moment of culmination, then our bearing would have been north or south. And then he would have come up, as we did in the previous method, with a true latitude. Now, in this case, our bearing is not exactly 100% north or south, so we will have to add corrections. And voila, we are also using our dead reckoning longitude. It's not a true longitude, it's a dead reckoning longitude that will tell us where to draw the line of position. So what we get there is a line of position, the yellow one being the line of position where our ship will be somewhere. Voila. Now, the latitude obtained by this method, as I already told you, it would be a true latitude, but okay, that would only be the case if we would be starting from not that reckoning longitude, but from a true longitude. It should also be noted that the position line, the one that we are drawing here, and the position to which to draw the position line is for the time of the observation. And the time of the observation is just before or after meridian passage. Voilà, so it's for the actual time of the observation and not for the moment of meridian passage. Voilà. These are two elements that you should take into account. Now, voila, this is actually then what we will be doing. You see here the apparent daily motion of the sun, being this one here. Voilà. And so you see that when the sun is in this position, that the sun is at meridian passage. Again, that is LAT 12 o'clock, and the sun is at its maximum altitude. Polar angle and local hour angle are 0 degrees. Now, when we observe the sun just before culmination, we see that, voila, H, the green line here, we see that the altitude just before culmination will be lower than the altitude at the moment of culmination. So we know that H in this case will be smaller than HO. On the other hand, if we take a look at the zenithal distance, we see that Z here, the zenithal distance, will be bigger than the zenithal distance at the actual moment of culmination. So in this case, we see here that Z will be bigger than ZO. ZO equals Z, the zenithal distance at culmination. We know that since the sun is here at the moment of culmination at its maximum altitude, we know that the zenithal distance at culmination is at its minimum. So it's the smallest zenithal distance that you have at the meridian passage. Voila. Now, this method for meridian passage, you see here at the moment of culmination, we have a maximum altitude, and at the moment of culmination, the true bearing will be either north or south. So this means 0 degrees or 190 degrees. Excuse me, I had to sneeze. So we know that at the moment of culmination, we are at a maximum altitude and our bearing will be at meridian passage, north or south. As I already told you, as we learned earlier, depending on our latitude and our declination, voila. So then we see here, if we do an observation in X-Meridian, when the sun is not really in the local meridian, just before or after meridian passage, we need to apply a correction to the altitude. We see here that the correction that we talk about is X, and that's being this one there, okay? Now, there are limits to this method. You can't use the method 2 hours before meridian passage or just till 2 hours after meridian passage. No, there are limits, and these limits can be found, I will explain that to you later on, in the Norris, in the nautical table, using this here, this certain pre-calculated value for A. Okay? The value for A depends on the LHA of the sun, of your celestial, or the LHA, let's say, in total, we always talk about the sun, but it's the LHA of your celestial body. Okay? Because the celestial body, the LHA actually is a value, if we transform this into time, LHA is an angle, 24 hours equals 360 degrees. And so the LHA varies over the day with a difference of 360 degrees from meridian passage to meridian passage, upper or lower or whatever. And so if we transform this LHA into time, you find the maximum values expressed as a coefficient, which we call A. And so the A is in function of the local hour angle, and so there are maximum limits prescribed in the nautical almanac for this value of A. So this means that in this case here, we can use the X-Meridian method when the sun is here, 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 or here, but we cannot use it when the sun is even further or even more before meridian passage or even more after this moment of meridian passage. So the only window or time window that you have, excuse me, is the one that you see here indicated by the orange line. Okay, and so how do you know this? By looking in your nautical almanac at the value of A. Voila. So again, this is represented here in another way. What do you see here? This is your celestial body before meridian passage. This is the celestial body at meridian passage. Voila. And so you see that you will have to apply corrections to either the altitude, and so you will see that you have to add the correction to the altitude, or you have to subtract the correction from your zenithal distance. Okay. And so if we project the sun here on the circle going from the zenith to the nadir, okay, you see here that this line here, that will be x, and that will be the correction factor that you have to either add to your altitude, so in this case it will be plus, or that you have to subtract from your zenithal distance, plus to the altitude and subtract from the zenithal distance. Voilà. And that is because the height of culmination will be at its maximum, so it will be bigger than the altitude just before culmination, and the zenithal distance at culmination is at its minimum, so it will be bigger just before culmination. And so x here is your correction factor. Voilà, here this is represented again in another way with a normal spherical triangle that we use. And so again, you see here z at culmination, z before culmination, and so you see here that x being the green line here, x is zenithal distance before culmination minus the zenithal distance at the moment of culmination. And voila, you know that normally when we are at the moment of meridian passage, that we can determine our true latitude by adding or subtracting declination from our zenithal distance. Voilà. And so what will we do here now with this method? How do we obtain the zenithal distance that we know from the previous recording? We know the zenithal distance is not something that we can observe. The only thing that we can observe is our altitude. Voilà. If we subtract the altitude from 90 degrees, then we get our zenithal distance. In this case, we will get a zenith distance before culmination, to which we have to apply corrections. In this case, we will have to, if we apply it to the zenithal distance, we will have to subtract the correction, because the zenithal distance before culmination will be bigger than the zenithal distance at the moment of culmination. So you have to subtract the correction to get a corrected zenithal distance. Okay, and so if we get the zenithal distance, we can determine our declination from the nautical almanac for the moment of our observation, which is this moment here, as I already told you, not the moment of meridian passage. And so then we can calculate our apparent latitude. It will not be a true latitude, as I already told you, because you're doing an observation that has to be corrected, and that you need that reckoning longitude. Okay. Voilà. Now, the formula that the X-Meridian method is based on is the formula here for calculating x. And x is the difference between zenithal distance before minus zenithal distance at culmination. Now, we know our estimated latitude, and in a nautical almanac, we can find the declination and we can determine our polar angle. We know the Greenwich hour angle, which we can transform into local hour angle with our direct reckoning longitude. And so the local hour angle can then be transformed into polar angle. We also know our altitude. That is what we measure with our sextant. And so this way, we can determine with our calculator the value for x. And if we know the correction that needs to be applied to our zenithal distance at the moment of observation before meridian passage, we can calculate the zenithal distance, the corrected zenithal distance for the moment of culmination. And voila, then we can use, again, the shortened formula being LA in this case is equal to the zenithal distance plus or minus the declination, or in some cases the declination minus the zenithal distance, depending on our latitude and our declination. The sign of the latitude and the declination and the value of the latitude and the declination. As you know, when if the declination is bigger than the latitude, then we have to apply this formula. Now, how can we determine this formula? Well, I'm not going to completely explain this to you. This is a mathematical story for a mathematical demonstration, of which the point is that we will determine the value for x. X, as you know, x is the difference between the zenithal distance before and the zenith distance at the moment of culmination. Now, the demonstration is included in this PowerPoint. You've all known these, well, you should all know these. I'm not going to ask it at the exam, that's what I mean, but if you read this demonstration, you should all be able to understand, because it's based on the cosine rule for the navigation triangle that you've learned in the first year during the course of mathematics. And so if we transform this via a long formula, adding, using the Simpson's formula, etc., then you finally end up with this formula here, okay, being the one that I showed you earlier, in which you know your estimated position, your declination, your altitude, and the polar angle, okay? And this is the formula that the X-Meridian tables in the Norris are based on, okay? So if you're interested, please read this demonstration. If you have questions, don't hesitate to ask them. But since I will not ask you this on the exam, I'm not going to waste my time entirely explaining you this demonstration. So the X-Meridian can be calculated using this formula. The X-Meridian method can be calculated using this formula. But in practice, what will we do? In practice, we will always referred to the X-Meridian tables that are already pre-calculated for you in the Norris. Okay. In the Norris, you will find 3 tables. You will find table 1, table 2, table 3, and actually there is even a 4th, but that I will explain to you later on. And so in the first table, maybe it's a wise thing to open your Norris. In the first table, you find the value for A. Remember, what was A about? A is the limiting value for determining how much time before and how much time after meridian passage you can use this X-Meridian method. And so I told you that this is based on the LHA of your celestial body, the hour angle of the celestial body, because that will indicate how much time before or after meridian passage your celestial body is in its apparent daily motion. And so here you find table A. There are 2 tables. There is a table for latitude and declination having the same name. And then on the other hand, there is a table for latitude and declination with a different name. Okay, so please make sure that you use the correct table 1. So attention, there are 2 pages, latitude and declination, same name, latitude and declination, different name. And how do you have to enter this table? First of all, you will have to use your latitude, and secondly, you will have to use your declination. Okay, so with these 2 elements, you will find the value for A. Okay, so depending on your declination and your latitude, you will find the value for A. Okay, and then with this value, what should you do? You should check if it's is it mentioned here. I will try to show you. Yeah, this is, you should go to table 4, and then you check in table 4 if you are within the limits for using the X-Meridian method. So if you are within the minutes of time allowed before or after meridian passage. Okay, and so determining on whether your dependent on the value of A, you will see what the maximum interval is of your observation. So if you have a value of A which equals 10, then you have a maximum interval of only 14 minutes before and after meridian passage that you can use the X-Meridian method. So you will have to check the time of your observation, and then you will have to determine what is the time of meridian passage. You will have to compare this with the time of your observation, and then you will have to make sure that you are within the maximum interval of minutes before or after meridian passage. Voilà. So this is what you do in the first place. Voilà. Then secondly, you will have to find corrections. The corrections can be found in table 2 and table 3. And the corrections, which are they actually? They are the X values that we calculated here, or that you can calculate here with this formula that I showed you here, okay? Which, if you're interested, you can completely derive from the formula in your spherical triangle. And so that is this formula here, that one there, where you find x as the correction and the value for a equals this elements here. So that is what is being calculated in the first table of the X-Meridian. So, and then in the second table, you will find the corrections. The corrections are actually in the formula equal to a multiplied by the square of the polar angle. But in the table, in the X-Meridian table, these corrections are pre-calculated for you and subdivided into two parts. The first part being x, the second part being x accent or something. The second correction always needs to be subtracted from the first correction. This is also mentioned in the tables. Okay? And then the idea is that finally what you do, you end up with your altitude, you add the first correction, you subtract the first correction, and then you get your corrected altitude, with which you then use the or calculate the zenith distance, the zenith distance at culmination corrected. Voila, then you add or subtract the declination, and this will give you then your apparent latitude. Okay. Now, voila, this I explained to you. A is the change of altitude of a body in seconds of arc during the minutes immediately preceding or following the meridian passage. Okay. There are some bands in which the value of A is omitted because there A changes too rapidly for actually being able to accurately interpolate, and that is when the body is almost near the zenith. Then this method cannot be used. Voilà. And as I told you, there are two tables, latitude and declination, same name, different name. And so, voila, this is, where is this table one? I want to show it to you again. So this is this table one, depending on your latitude and your declination. First of all, if you continue the exercise, check if the A is within the limits stated in table 4, excuse me. Okay, then we go to table 2, where we find the first correction. In table 2, we find X. And so you see here, all the information is mentioned in the tables. They say at upper transit, you need to add the reduction to the true altitude. So this means we know when we are, voila, this is meridian passage. When we are before meridian passage, this is H culmination, H observed. We know that we will have to add X. I'll use a blue letter, a blue color. We have to add X to our observed altitude, and so this is what is mentioned here. The observed altitude becomes the true altitude after correction, of course. And so we have to add the correction to the altitude, or you can also subtract the correction from the zenith distance. So based on your value that you found in table A, table 1 for A, and your local hour angle, you will have to add a certain amount of minutes to the altitude that you have observed, okay? Because your altitude will increase towards meridian passage and then afterwards decrease again. So this is what you find in table 2, and then table 3 contains a second correction, but that is only to be used when the first correction is above a certain value that you can see here. When it's more than 15 minutes, depending on the altitude of your observation and your first correction, you will find a second correction, which will always needs to be subtracted. So that's what I told you. The total correction is always X minus X accent. And so the total correction will have to be added to your HV or subtracted from the zenith distance. And so this is how we will use this X-Meridian method. This is the schedule that you can use, or the system that you can use. I think it's a good idea if we do an example. So On the 25th of October 2020, at a latitude of 49 degrees north and a longitude of 35 degrees 20.0 west, we do an observation of the sun's lower limb, and we find there an instrument height of 27 degrees 58.2. Our index error is is 1.2 of the arc. We know when it's off, put it on, that you know, so the correction will be positive. Our height of the eye is 10 meters, watch time 12:14, chronometer time 2:40:55. So the first thing to do is to determine whether the chronometer time is 2 o'clock or 1400. How do we do this? We take our watch time, which is 12:14, and we transform our longitude, being this one here, into time. How do we do this? We do this with the conversion of arc to time. You can also do this with your calculator. We know that 30 degrees is 2 hours plus 5 degrees 20 minutes. This gives us in total a longitude transformed into time of 2 hours, 21 minutes and 20 seconds. We are in the, where are we? In the west. So we know that Greenwich is west. So this means that we have to add this longitude transformed into time. That is correct, we're in the west. So we add this. So this gives us then an approximate GMT of 14:35:20. And so now we know that, voila, our chronometer time, that we need to add 12 hours. Our correction was 0. We add 12 hours, so we get a universal time, or a GMT, of 14:40:55. And so at that time, we will calculate our GHA. Okay? If we then find the GHA of the sun, we see that at that time, the GHA is 33 degrees 59.9. I suggest that you take your nautical almanac on the 25th of October, and so there you will see that the GHA of the sun at 1400 hours is 33 degrees. The 25th of October at 1400 is 32 degrees 59.9. Voila, that is correct. Now that is the GHA at 1400. We need to add increments for our additional 40 minutes 55. These increments correspond with the value that you see here. Increments are always to be added, so we get a total GHA of the sun of 44 degrees 13.7. But we want to transform this into our LHA, because that is what we will need in the X-Meridian tables. So we are in the west. This means that Greenwich is west, so we have to, in this case, subtract our longitude of 35 degrees 20, and this gives us then an LHA, a local hour angle of 8 degrees 53.7. Since our LHA is smaller than 180 degrees, we know from, we explained that already a couple of times, that the polar angle will be west, and the west will be in the front column. So, in this case, our LHA is equal to our polar angle, which is west. And then another thing that we need for the X-Meridian tables is the declination. So we go again to our nautical almanac, and there we find a declination of 12 degrees 22.8 south. Our D value can be found at the bottom of the page. It's 0.9, and so by inspection we see that, we call it by inspection, we see that the value of the declination is increasing towards the south. So voila, 0.9 for 60 minutes corresponds with 0.6 for 40 minutes. And so we have to add this 0.6. This gives us then a total declination of 12 degrees 23.4. And so now, we have now our LHA, we have our polar angle. Another thing that we need is, voila, we need our true altitude. I told you that the altitude that you observed with your sextant just before culmination is 2758.2. Our index correction is 01.2, so that we add to get an observed altitude. And the observed altitude needs to be corrected for the dip and the total correction. The dip is minus 5.6 because we are at an A of 10 meters. So we subtract 5.6, and then the total correction can be found on the first pages of the Nautical Almanac. For the sun, lower limb, we get a total correction of plus 14.4. And this gives us then the corrected true altitude. So our instrument height has been corrected, and we obtain now a true altitude at the moment of observation. So the altitude that we corrected here is we are probably after meridian passage, as I see here. So the altitude that we have corrected here will be, or have calculated here, will be this one. Okay, and so we see now that the corrections that we need to apply are this one here. So you either try to calculate now the correction and add it to the HV, or subtract it from the zenith distance. In this case, what have I done? I have immediately subtracted my altitude of 90 degrees to get a zenith distance at the moment of our observation. And so we have to subtract, in this case, the correction from our zenith distance. If we go to table 1, we see there that with a declination of, what was our declination, 12 degrees, something, 1223, and a latitude of, what was my latitude? It was 49 degrees. So we need to be somewhere here, 49 degrees, or somewhere here, that's the same thing. And at a declination of 1223, we see that we have to interpolate between 142 and 146, so we get a value of A of approximately 144. Okay, with this value, we go to our second table to determine X, and we go to table 3 to determine X accent. But the first thing that we need to do now is to check whether we are within the limits of our meridional passage. Okay, and so with the value of A 1.44, we go to table 4. A is 1.44, so that is somewhere here. And so we see that our maximum interval is approximately 52 minutes. So how do we check this now? We go to the page of the 25th of October, if I'm not mistaken. And so at the 25th of October, we see that meridian passage is, we see this in the pages of our Nautical Almanac. We see that meridian passage is LNT 25th 1144. Voila. If we want to transform this into GT, because we want to compare this with our chronometer time, what do we have to do? We have to go again to what we calculated in the beginning, to our G transformed into time, which is 2 hours 21:20. Our longitude was, what was it? Our longitude was west. So Greenwich is best. So what do? We add this. So this gives 05, 12, 14. And so we see that our GMT is 14:05:20. That's the GMT of meridian passage. We did our observation at, what was our chronometer time? It was 14:40:55. So we see that we are within the limit of 52 minutes for our observation. So we say, okay, we can use the meridian passage method. Okay, So now we go to table 2 to determine our correction. And so our local hour angle is needed here, and the first correction. The first correction was 144. So we have to interpolate somewhere here and here. And this gives us then, because our local hour angle is 8 degrees 53, if I'm not mistaken. And so this gives us then, if we do the interpolation here, and then like that, this gives us then a value of 29.4. Well, and so this correction has to be subtracted from our zenithal distance or add to the true altitude. Voilà. Then we go to the second correction. Our first correction was, well, I didn't include the table here apparently. The first correction was 29.4. And so if you look this up in table 3, you find there that the second correction is plus 0.1. Okay, if you have trouble finding this, don't hesitate to ask. I will show you this during the live sessions. And voila, so if we subtract this correction from our zenithal distance at the moment of observation, then we get here the zenithal distance at the moment of culmination. And so then we can simply just apply the normal procedure as we did for meridian passage. We subtract here in this case our declination because our latitude is probably north, as I presume, yeah. And our declination is south, so we have to subtract the declination from the zenithal distance in order to get our true latitude. Okay, again, if you want, we can, it becomes a little bit complicated like this, but what can we do? We can make this small drawing. If you don't know this anymore, what can you do? You can make the small drawing as I explained to you earlier. Voila. You say, okay, here, this is the equator. Our latitude is north, so that is where you are. That is where your ship is. This is the declination of the sun. So this is your latitude. This is the declination. So, and this is the zenithal distance. Okay, so we see here that in order to obtain the latitude, what should we do? We should take the zenithal distance and subtract our declination in order to obtain the latitude. Voilà. And so, quod erat demonstrandum, our latitude and our declination have different names, so we have to subtract the declination from the zenithal distance. Voilà. And so this will give us then our calculated or apparent latitude, which is 84 degrees 59.6. Compared to our dead reckoning position, 49 degrees. Voilà, this is a quite good observation that has been done. Voilà. And it would have been very more or less near meridian passage. Okay, but as I explained to you, we now have obtained our calculated latitude. This is not the actual latitude that our ship will be on. What we need to do now is we need to determine the true bearing. Okay, and so we can determine this true bearing by calculating an azimuth. You know that we can calculate the azimuth in 3 different ways. I'm not going through the whole process of explaining this to you once again because we did an exercise on this during a previous recording. You can calculate the azimuth with the ABC tables. Voila, that is what you see here. Or you can calculate the azimuth with a combination of the ABC tables and your calculator. So you can calculate yourself if you're scared of the ABC tables, because I see that some of you are. And you can calculate the tangent of the latitude divided by the tangent of your polar angle. This gives you 735. You can calculate B, which gives you 142. And so, voila, now the only thing that you need to do is to determine the signs here. They are both south. So this means that you have to add A plus B in order to obtain C. And then if you put C in this formula, then you get an azimuth, which is south 9 degrees 51.6 west. Okay, and voila, as you know, the azimuth takes the sign of the C factor and the sign of we should all say this together, the polar angle. Okay, and then so you transform this into a true bearing, and so the true bearing at the time of your observation is 189 degrees 51.6. You know that there is also a third method of calculating your true bearing, that is with this formula here, where you obtain the azimuth angle via the cotangent of the azimuth with the same elements here, this one being A, this one being B. You multiply it by the cosine of L. And then you see that here you get, because the declination is considered as a negative value because it's south, so you get a negative angle, but in a spherical triangle, this means that you will have to add 180 degrees. And so again, you take the same signs, you get an azimuth angle north 170 degrees point something west. And so this means that your true bearing again will be 189 degrees 51.6. So what have we calculated now? We know now our bearing. And so what did we do? This is what I explained to you in the beginning, or tried to explain to you in the beginning. You start from your, I will use another color, from your dead reckoning position. Okay, so we have a dead reckoning longitude, which is GE. Okay, and so then you calculate, that is what we have done here, you calculate your calculated latitude or apparent latitude. That one you indicate on your chart. I will use the green color for that one. So you get your calculated latitude. But as I told you, this is not the position, the line that your ship will be on. It would have been the line that your ship would be on if you would have taken true latitude at meridian passage, or if your dead reckoning longitude would have been correct. Unfortunately, this is not the case. So what should you do? You should additionally also still calculate your true bearing. We calculated the true bearing, which is 189 degrees. So this is something like the purple line. And so where do you indicate this true bearing? You indicate it at the point excuse me. Where was I? What should you do? Where do you have to indicate your true bearing line? You have to indicate it at the point where your calculated latitude intersects your dead reckoning longitude. So, and that is this point. And so starting from that point, you draw your true bearing, and perpendicular to the true bearing, you find your line of position. And that is the position where your ship will be at, or where your ship will be on. Okay. Well, actually, this is nothing else than, this is a shortened method actually for an intercept. Okay. What you also could have done was, okay, you calculate your, I will erase all the rest here. This is just to try to make it a little bit clearer to you, or try to tell you what this method is about. What you also could have done was, you could have calculated here, if you have the true altitude, and then what you can do, you can also calculate with the formula that I explained to you earlier, the calculated altitude. And if you then compare the true altitude to the calculated altitude, you get the delta H. Voila. And then what do? This is the delta H is your intercept. And so what do you do then? Then you calculate your true bearing. And then starting from your dead reckoning position, you could have indicated the true bearing on which you mark your intercept. Voila. And so this is what you could have done. If this, for example, would have been your LE and GE, what could you have done? You could have indicated your true bearing, then mark the intercept, and starting from this point, perpendicular to the intercept, indicate your line of position. Voila. But this is a longer method, and so voila. You can use the X-Meridian tables to use the shortened formula being LV or LA is Zenith Distance minus the plus or minus the declination. Voilà. Okay, so voila. When should we use this method? To recapitulate, the method is actually the most accurate when the azimuth of the object is near the north or the south. And so when is your azimuth or your true bearing north or south at the moment of meridian passage? You know there is an interval defined by the factor A, which gives you a limit value for LHA. And in table 4, you find this LHA already converted into time. And this will give you then the limit value between which limits you can use the X-Meridian table. And so when the azimuth changes east or west, that is actually, normally you have a true latitude. This is a position line perpendicular to a true bearing, north or south. But if your true bearing diverges from this north or south and changes to the east or to the west, something like that, it should be, this is one dot, you see that then there you get an angle between the north-south bearing and your actual bearing at the moment of meridian passage. And the more you deviate from the east or the more you deviate from the west, the bigger these angles get and the more uncertainty you get. We talked about this when we talked about errors in the intercept method. And so that is what this is based on. So that is why there are limiting values for this method. Okay, so these methods are a quick and easy way to correct the altitude, as I already told you, when the object is fairly low in the sky. Because when the altitude gets bigger near the zenith, then the changes are going too quick, and then it's less accurate. The corrections that you apply are more difficult to calculate and less accurate. Okay, and so it's a method when the observer has missed noon by a few minutes. Voilà. So this is the second method for determining your true latitude near the moment of meridian passage. The first one being calculating your latitude at the actual moment of meridian passage. The second one being within a specified time limit before or after meridian passage. With this method, you can either calculate the apparent latitude or the corrected latitude just before or just after meridian passage. Okay. Voila. Okay. Now there is also a third method for determining your latitude, a third short and easy method for determining your latitude, and that is by using Polaris. We know that Polaris is a star which is close to our North Pole. And it's not really actually on our North Celestial Pole. It circles around the North Celestial Pole at approximately with a radius of approximately 1 degree. Okay, but this means that it's circling around our North Celestial Pole with a distance of approximately 60 miles. The pole itself, about which Polaris goes, actually indicates the true north. And if Polaris would really coincide with the North Celestial Pole, then the altitude of Polaris would be equal to the observer. I will show you pictures of that later on. That will make it more clear. But unfortunately, we are not that lucky. The pole star is not exactly coinciding with our North Celestial Pole. It circles around it. So we need to apply corrections to the altitude of Polaris in order to be able to determine our latitude. Voilà. Now, we know that Polaris is a very distant star from the Earth. It's located in a position very near the celestial pole, but not on the actual celestial pole. Okay. Now, if the axis, if the Earth's axis would be projected into space above the North Pole, it points to the North Celestial Pole, that we all know, and it's the axis around which the Earth rotates. Now, Polaris is located almost exactly at that North Celestial Pole, so at the center of the spin. So it appears to our eyes of the observers on the Earth that Polaris stays in the same place. But what actually, and it appears to us that stars that are further away from the North Celestial Pole, that they are thought to move in circles around Polaris, viewed from the Earth during the daily rotation of the Earth. But in fact, Polaris lies a short distance away from the Earth's axis, about 1 degree, as I already told you. So we know that Polaris actually does move a little, because if this is the North Celestial Pole, if Polaris would have been here and the Earth circles around its axis, it would seem as if Polaris would always stay in the same place. But in reality, Polaris is not on the celestial pole. It's at 1 degree, 60 miles distance. So actually, it seems as if Polaris is also having an apparent daily motion. So it does really move a little. And it traces a small arc in the sky around which all the other stars, all the other visible stars, make wider circles. Okay, and so this is if you would be able to take a picture of the movement of the stars, you would see that all the other stars are circling around Polaris with a frequency of 23 hours and 56 minutes, being a sidereal day. So this is what I told you here. If this would be the North Celestial Pole, the star Polaris would be here. And so normally if the star would be in the direction of the North Celestial Pole, it would seem as if it stays in the same location. But since it's not in the same location and it's at a small arc away from the North Celestial Pole, it seems as if it's also moving and marking a circle around the North Celestial Pole. Okay, and so this actually, if you want to draw this on our celestial sphere, voila, this would be our zenith and our nadir. This is the equator. So let's say that this is the North Pole, the South Pole. If the star would be here, there would be no apparent daily motion. But since the star is somewhere, this is a little bit exaggerated, since the star is, the Polaris is somewhere here, Polaris also has an apparent daily motion like this. Okay, and so it does circle Polaris, around Polaris, with a radius of approximately 60 miles or 1 degree. Polaris is moving. Polaris is moving because of its because it's not on the north, exactly on the North Pole, but it is also moving closer and further away from the celestial pole due to the Earth's actual precession. We know that the Earth, the axis of the Earth also moves due to the gravitational forces of the Sun and the Moon, and this movement of the Earth's axis that we call precession. And it's because of this precession that we have the impression that Polaris actually is moving closer and further away from the celestial pole. Okay. Due to this precession, the closest approach of Polaris to the North Celestial Pole will be, that is calculated on the 24th of March, 2100. Voila, and its declination then will be 89 degrees, 32.50. So this means that this is the closest point that Polaris will ever get to the North Celestial Pole. Okay. Now this goes in cycles as well. We know that one precession cycle of the Earth's axis is shifting in about 26,000 years. So voila, the movement of Polaris and all the other stars around it will have the same cycle. Now, how can we find Polaris? We also know that Polaris is the brightest star of Ursa. I forgot my S there. Minor. And so, what do you need to do? If you have Ursa Major that you know, you take these two stars here, you take 5 times the distance, and then you will find Polaris. Well, I'm sure they explained this to you already in other classes. Again, this is the influence of the gravitational forces on the Moon and the Sun, which cause the Earth's pole to precess over a period of 26,000 years, as I explained to you. And so the North Celestial Pole will align itself over the time toward various stars. Okay, now at this time it is Polaris, but they say that 12,000 years from now it will be much nearer Vega, and so Vega can or could be considered as the North Star. Okay, voila. Now I told you that we can use the North Star in order to determine our latitude. This is illustrated by the pictures that you see here. If we would be on the equator, we would see Polaris at an altitude of 0 degrees. So Polaris would actually be at an altitude of 0 degrees. If we would be on the North Pole, on the other hand, here, then Polaris would be directly overhead at an altitude of 90 degrees. And so we see that when you are at the equator, our latitude is 0 degrees, and the altitude of Polaris is also 0 degrees. When we are at the poles, our latitude is 90 degrees, and our altitude of Polaris will be observed with the sextant, will be also 90 degrees, because Polaris will be more or less I say, because we need to correct it, directly overhead. Okay, so this means that if we are at a latitude of 30 degrees, that the altitude of Polaris here above our horizon will also be 30 degrees. Okay, their latitude is 30 degrees and our altitude equals 30 degrees. And this goes for all latitudes in the Northern Hemisphere. You can only use this method because Polaris, unfortunately, is only visible in the Northern Hemisphere, and as up to now, there hasn't been determined a South Star which coincides more or less with the South Celestial Pole. So this means that as you travel to the north, if you go more to the North Pole, that the altitude of Polaris increases, and so does your latitude. If you travel to the south, to the equator, then the altitude of Polaris will decrease, and so will your latitude. As we go east or west, the altitude of Polaris doesn't change. Now, there are two ways to determine our latitude by determining the altitude of Polaris, or the height of Polaris. First, you can do this via a very complicated mathematical formula, or you can do this using the nautical almanac, which is what we will do in practice. Now, again, here there is a complete demonstration of the formula that we use for calculating Polaris, or latitude using Polaris. Again, please, if you're interested, don't hesitate to take a look at this demonstration, but I will not waste my time using, because you see it's a very long demonstration here, and using all kinds of mathematical calculations. Those of you who want to take a look at it, please don't hesitate to do so. Ask me questions during the live chat sessions if you want. But the basic idea is, again, here, that we will calculate our latitude. How? We will do it by determining the altitude with our sextant. We get an index, an instrument height that we transform via all kinds of corrections to a true altitude. And then we have to subtract or add corrections. In this case, we will have to add correction A0 and A1 if you want to use the formula. And so in this demonstration, we will first of all calculate A0, as you can see here. And then we will calculate the second correction, A1, being this one here. And that we then apply to our altitude that we observed. We apply correction A1 and A2 in order to obtain our latitude. If you have questions about this demonstration, I'll be available during the live sessions, but normally everything should be well explained. But as I told you, don't spend your time learning this complete demonstration by heart, because I will not be asking you this during the examination. Voila. Now, we switch to the practical way of determining Polaris, which is by using the tables pre-calculated for you in the nautical almanac. Okay. There we have a formula, which is this one here, which allows you to calculate your latitude using your observed altitude. And how do you do this? First, you have to subtract 1 degree and then add 3 corrections, A0, A1, and A2. Now, the 3 corrections, what are they based on? The first correction, A0, is in function of the local hour angle of Aries. Okay. Now, and this first correction is calculated for mean values of the SHA of Aries for the year. In this case, if you go to the nautical almanac, it will be for the year 2020. And voila, there you find the value for A0 for mean values of an SHA of the value that you see here and a declination of 89 degrees 21 and at an assumed latitude of 50 degrees. The correction that you get there, in order to keep it always positive, for calculation methods, this is easier. What they do, you have to add a constant value. Well, you don't have to do this, it's added to the correction in the tables of the nautical almanac. You have to add a constant value of 58.8. Well, that is the first correction in function of the LHA of Aries. The second correction is in function of the LHA and your latitude. It's actually a correction for assuming that your latitude was 50 degrees. And so this correction needs to be increased by a constant 0.6, again, in order to make it always positive. Then you get correction A2, which is in function of the LHA of Aries and the date. This is again a correction for the mean values that you use here for SHA and declination. That will determine your position of Polaris. And again, this will have to be increased by a constant value of 0.6. So this means that you have correction A0 plus A1 plus A2. And in this correction, you have added 58.8. You have added 0.6 and 0.6. So in total, this makes a constant of 1 degree that has been added. So in the end, for the correction, you have to subtract this 1 degree. You apply all these corrections to your observed and corrected, in this case, altitude, and this will give you then your latitude. So you observe with your sextant the altitude of Polaris. If Polaris would have been on your north celestial pole, your latitude would have been equal to your altitude, but in this case, this is not correct. Polaris has an apparent daily motion, so you can predict the path of Polaris, and this path is predicted by values for the SHA in your declination. And so you need to correct the altitude that you have obtained for Polaris. You have to add corrections in function of latitude, local hour angle, and date, which are A0, A1, and A2. And then you have to subtract 1 degree. And this 1 degree has nothing to do with the fact that Aries is at 1 degree approximately from the North Pole. No, this is due to the corrections that you have to, that they have applied there in the tables for Polaris in order to keep all these corrections here, A0, A1, and A2 positive. Voilà. And so in function of the LHA of the first correction table is in function of the LHA of Aries. How do we calculate this LHA of Aries? We know the time of our observation. For that time, we can determine the GHA of Aries, and then if we have our longitude, we can transform this into LHA of Aries. And so on this drawing here, you can also see that if this is the first point of Aries, you have the SHA of Polaris. If you add the LHA of Aries, then you get the LHA of Polaris. That is what we have learned in previous lessons. Now, the procedure is, first of all, obtain the universal time of your observation, and then you find the GHA of Aries. The GHA of Aries is transformed into LHA, and so with this LHA, you can go to table 1 to find A0. Wait, excuse me. Okay. Then you can go to table 2 to find A1, and to table 2 Can go to table 1 to find, or the first correction table to find A0, then you find A1, and then the third correction is A2. Okay, all these corrections need to be added, but in the end you have to subtract 1 degree, because all these corrections are always positive. Because constants have been added, you have to subtract 1 degree. Voilà. Okay, these are the corrections tables for Polaris. We'll make an exercise in a few minutes. So these are the correction tables used for determining latitude with your sextant altitude from Polaris. So the first table is in function of the LHA of Arias that we get from the nautical almanac. We know the GHA, we apply our longitude, and this gives us then our LHA of Arias at the time of the observation. Okay. So if we have, for example, an LHA of I don't know what, 35 degrees, then you have to go to this column and to the line of 5 degrees, and so this will be your correction. And then you go down the same column with your latitude, because this is for an assumed latitude of 50 degrees south. Now you have to apply a correction for the latitude. If your latitude is 50 degrees, oh no, let's say not 50 degrees, that may be a little bit confusing. If your latitude is 30 degrees, the second correction, this is A0, then you find the second correction of 0.6 for A1. And then the third correction, because we took the mean values of SHA for Polaris and declination, we have to apply a correction for the time of our observation, being the month. Let's say we are in June, then our correction will be 0.2. And so the formula, again, you don't need to learn anything by heart, certainly not for the exercises. The formula is what you find there. Apparent altitude corrected for refraction, so this means HV, minus 1 degree plus all the corrections. And so for the first table, you have to interpolate. For these tables, second and third correction table, you don't need to interpolate. So here are some examples. I think it's maybe best if we do an example together. We do an observation on the 7th of September. Our watch time and chronometer time are given. We know our estimated latitude and longitude. And so chrono correction, altitude of the eye, index correction are given, and our instrument height we observed with our sextant is 50 degrees, 48.8. And what is required? Determine your true latitude by Polaris. So we are on the 7th of September, if that is correct, yeah. Our watch time of observation was 1:57, voila. Now, we need to determine whether our chronometer time is 6 or 1800 hours. We do that by applying our longitude, transforming our longitude into time. That is approximately 7 hours 48. No, this. We transform our longitude into time. And since we are in the east, we know that Greenwich is least, so we have to subtract. And so we do our observation at 18:08:12, the previous day. Very important. So we know now that our chronometer time, we need to add the correction and 12 hours. Well, and so at that time, we determine the GHA of Arias. We apply our longitude, and this will give us then the LHA of Arias, because that is what we need in the Polaris correction tables. Our longitude is 170 degrees, 12.0 east. We are in the east, so Greenwich is least, so we have to add our longitude in order to obtain our LHA. And so this gives us 337 degrees, 29.0, if I'm not mistaken, yeah. 256. Yeah, this 373. Voila, and so we subtract again 360 degrees, so this gives us 13 degrees. So we know our LHA. Now, what should we do? We want to compare our altitude to our latitude. So first of all, we need to determine our true altitude. So we have our index instrument height. We apply the index correction. In this case, it is positive, 3 seconds. So we add that. We subtract 6.3 for the dip. This gives us the apparent altitude, and then we apply a total correction for stars, which is minus 8 seconds. Voila. And so this way we obtain a true altitude of 50 degrees, 38.2. And then we go to our Polaris correction table with our LHA, which is 13 degrees. I'll try to find the correction table again. So our LHA is 13 degrees. What was it? 13 degrees something? 29. So that's easy for the interpolation. So we find here the table 10 up to 19. So this gives us 13 here. We go to the 3, and there we find a value of 24.3 and 24. So this gives us 24. 24 point. That's why I'm hesitating a little bit. Or LHA, what was it? I think I forgot to correct this. 13 degrees 29. So voila, probably I changed for the new date, but probably I didn't change it completely. So voila, it should be 24 degrees between 13 and 14. So it should be 24 degrees voila, 0.1 or something. Okay, so please pay attention. This should be corrected. I didn't notice this. It should be 24 degrees 0.1. Okay, then we go down to the same column. We have a latitude of, to go again, 50 degrees. So we go down to the same column where we, at the latitude of 15 degrees, we find a correction value of 0.6. So this is A0, this is A1. And then we go down again. I think we were in September, if I'm not mistaken. Is that correct? That's September. So for the month of September, we find a value of 0.5. So we have to take 0.6. Oh no, now I see it. Probably it was correct. I'm sorry. Now I see it. These are correction tables for Polaris. Well, that's maybe already a good example, or a good reason, a good thing for you to know. The Polaris correction tables, they change. Okay, and so voila, the tables that I included here, it was just by means of example to show you these are the tables for 2016. So voila, I didn't make a mistake. I'm sorry. The values that you see here in the table are correct, but since the correction tables for Polaris change every year, and why do they change? You know that by now, because it's based on the mean value of the SHA and the declination for that year. This year it will be 2020, so the correction values each year change. Voilà. So we go again to our corrections. A0, if we use the correct table for 2020, if you look it up in your nautical almanac, you will find that it's 25.4, and that the correction for A1 will be 0.6 and 0.5. All these corrections are to be added, and then afterwards you have to subtract 1 degree. And so this gives you then a true latitude of 50 degrees 04.7. Okay, so you determine in universal time your time of observation. With that, you find your local hour angle of Arias, because that was what you need in the Polaris correction tables. You transform your observed altitude into a true altitude. That is the formula that is mentioned here. This I can show you in this table. So you take the apparent altitude corrected for refraction, that is your true altitude. And so to that altitude, you have to apply the corrections A0, A1, and A2. A0 in function of the LHA, A1 in function of the latitude, and A2 in function of the month. And then because of all the constants you've added, you need to subtract 1 degree, and this will give you then your true latitude. Voilà. So That's it for this recording. Should you have any questions, I'll be available during the scheduled course hours on Friday morning, so don't hesitate to ask me questions. Good luck.